Welcome back everyone to a session on automata theory and computability. This lecture video will be the continuation of the previous one, where we have seen the ambiguity in context-free grammar. And then in this lecture video, we will learn how to reduce ambiguity in the grammar. So we have to identify the techniques of reducing ambiguous. So before that, we have to see what is the source of ambiguity in a grammar. Okay. For that, we have to take an example, and let us consider the example of balanced parentheses. Okay, so I have these three rules, right? SQs, opening bracket, S, opening bracket, S, and closing bracket, SQs, SS, and SQs epsilon. Okay, so one source of ambiguity is having a rule like SQs epsilon, that is a non-terminal giving epsilon is one of the source of ambiguous. Okay, so let me elaborate this. Now I want to generate this string, a simple opening and closing bracket. So this can be easily obtained by applying this rule, or opening S, close, and then what I will do, so this is the rule applied, SQs, right? Then what I will do, I will replace this S with epsilon. So that what do I get? I get simple opening and closing bracket. Okay, this is a simple way of deriving single opening and closing bracket. But what I can do is I can evaluate this in another way. Okay, so what I will do, I will apply the rule SQs SS, and I am following leftmost derivation. Okay, so the leftmost non-terminal, what I will do is I will evaluate it to epsilon. Okay, so I will apply the rule SQs epsilon. So what do I get? I end up getting single S, right? Now this S again I will replace it with 2S. Okay, so the applied rule is SQs, and now I will replace this S, the leftmost S, with epsilon. So I ended up getting single S. Okay, I can still continue doing this, right? So this S again I will replace with SS. Sorry, this applied rule is SS. Now again further I will replace it with epsilon. So I have single S. Now I am tired of making use of repetitive SS and epsilon. Now what I will do, I will replace this with opening closing bracket. Okay, rule applied is SQs. Okay, now I will evaluate this to epsilon. I got this. Okay, so this is how again another way I was able to generate this. So what I have done is I have made use of this rule SQs SS and replaced the S with epsilon, right? So this is a huge source of ambiguity, because I can generate any number of S with this rule, and I can eliminate these S by applying SQs epsilon rule, and whatever the S I have generated, unnecessary S, whatever that is generated, is wiped out without any trace, right? So having epsilon rule is one of the main source of ambiguity in the grammar. So this need to be addressed, right? So I need to have some technique of reducing or eliminating epsilon rules. Okay, so this is one technique what I need to incorporate to remove or to reduce the ambiguity in the grammar, epsilon rules, right? Okay, now the other one is having symmetry in my rule. Okay, so do we have a symmetric rule? Yes, we have. So here on the right hand side, the non-terminal is giving SS. So if I read this from left to right or from right to left, I have the symmetry, right? SS is a symmetry. I have symmetry here. So this is also another source of ambiguity. So to elaborate this, I'll consider one example. For that, I will first remove this. Okay, now let us consider an example of generating this string. S gives 3 opening and closing bracket pairs. Okay, so this can be obtained by having multiple parse trees, right? So what rule I have to apply? I will apply SS. Okay, the first S I will replace it with again SS, and this S I will replace it with opening. Okay, now I will make use of epsilon rule. Okay, so I have generated this. Now leftmost derivation again, epsilon. So this again, this is generated, and finally I will apply SS here, opening, closing. So I was able to generate this using this rule, this string using this rule, and I could have also applied another rule or another method of expansion, SS, and I will make use of opening S, closing bracket. Okay, replace this with epsilon. So in this case, I was able to generate this. Okay, now 2 more to go. What I will do, I will make use of SS rule again. Replace this S with opening S and closing bracket. Make use of S gives epsilon rules. Okay, so even this is done. Okay, so this S is replaced with the rule S, opening S, closing bracket. Now I will apply epsilon. Okay. So here also I was able to generate this string, right? So I have 2 parse tree for the leftmost derivation, which will be able to generate this string, right? So this is a problem because I had symmetry in my rule, right? So this is because I had a rule S gives SS. So this is another source of ambiguity in my grammar. So what I have to do? I have to eliminate this symmetric rules. So we have seen what are the sources of having ambiguity in the context-free grammar, and how it can be reduced, right? So this can be reduced by eliminating epsilon rules and eliminating symmetric rules. Okay, so we will see each of these in detail soon. Okay, so these are the 2 techniques of reducing ambiguity. So we will consider different examples of eliminating epsilon rules. For eliminating epsilon rules, because it is further required in converting grammar into normal forms. Okay, so this is very important. This concept is very important. First, let us eliminate epsilon rules. So for that, I have considered this particular example. Let us not bother about what this what this grammar will generate. Okay, so we will apply some epsilon eliminating method to make this grammar free of epsilon rules. Okay, so for that I have to identify nullable variables. Okay, so I have to identify what are the non-terminals that are nullable. So I should have a nullable set which initially will be empty. And what makes any non-terminal nullable? So we have, if there is a rule of this kind, okay, x gives epsilon, so this is producing epsilon, so that makes x as nullable. This is one way. The other rule is, if x produces non-terminals p, q, r, just an example, and if p, q and r, if all these 3 on the right hand side, all the non-terminals here, if it is a nullable, then x becomes nullable. Okay, so if only p and q are nullable and if r is not nullable, then x will not be a nullable non-terminal. Okay, so to identify nullable set, we need to have multiple passes on the rules of the grammar. Okay, so let us solve this particular problem. Let us identify the nullable set, and after identifying the nullable non-terminals, we have to remove it from the rule set to make it free from epsilon rules. Okay, so let me write pass 0. So this will be the initial nullable set value, which is empty. Okay. Now in pass 1, I have to look for rules of this kind, right, or this kind. So I have to see one by one all the rules, starting with the starting non-terminal. Okay, so this is of not of that type. This doesn't produce epsilon, so this is S is not nullable. Whether T is nullable? No. Okay, A is also not nullable, doesn't produce epsilon. B is also not nullable. What about this one? C gives C. Yeah, this is not nullable, but it also produces C gives epsilon, right? So that makes C as a nullable non-terminal. So what I have to do? I have to add this C in the nullable set. Okay, so this will be the value of nullable set after pass 1. Okay, so I have to repeat this passes until there is no change in the nullable set from the previous iteration or previous pass. So since there is a change now, I have to continue. So in pass 2, let me see what will be the nullable set value. Okay, S gives A T A, this is not nullable. T gives A B C. Yes, of course C is nullable, but A and B are not. For time being, it is not. So T will remain as not nullable in pass 2. What about A gives AA? Okay, this part it will A I can consider as a not nullable, but it also gives capital letter C, right? So this is A gives C. This is an OR symbol. So there are two rules for A. So A gives C. This makes A as nullable, right? So if I apply this rule, everything on the right is nullable since there is only one non-terminal here. S gives A gives C, right? So I can C is nullable, so that makes A as nullable. Okay, so what I have to do? I have to add A at the end of this iteration to the nullable set. What about B gives? Yeah, the same concept is applicable here. B also becomes nullable because it gives C, which happens to be a nullable non-terminal, right? And C was previously added, so no change there. So what will happen? I'll get A, B and C as nullable set. Okay, since there is a change in pass nullable value set from previous pass to this pass, I have to continue, right? So pass 3. Yes, in the next pass again I will check. S gives ATA, not nullable. S will remain not nullable. What about T gives ABC? What about this one? See, A is nullable from the previous pass, B is nullable, C is also nullable. So I can directly apply or relate to this particular rule, right? X gives PQR, and it is not necessary that I need to have 3. So simply talking about, in just an example where I had written PQR, I could have written multiple non-terminal also, or could have written only one. Okay, so that doesn't matter. If everything on the right hand side of the rule, if it is nullable, then automatically the left non-terminal becomes nullable. Okay, so in this case A, B, C, all 3 are nullable, so that makes T as nullable. Okay, this we have already seen, no changes here. So what I have to do, at the end of pass 3, I have to add a T here, right? So should I continue with one more pass? Yes, because there is a change in the nullable set. Okay, pass 4. First rule, ATA. So here everything on the right hand side is not nullable because I have two terminals appearing here, right? So it is S doesn't give only non-terminals, right? So this makes S as a not nullable. So the S will remain as not nullable even though T is nullable, right? Okay, because the S will not directly produce epsilon, neither indirectly it will produce epsilon, right? So I cannot add S to a nullable set, and no changes here. So what will be the value? I'll get A, B, C and T. Okay, now if you observe, the value of nullable set from the previous pass, that is pass 3, is same as the value of nullable after pass 4, right? So if this is the case, then I have to stop the iteration. So finally I got the nullable set value, which is A, B, C and T. So these are the 4 non-terminals that are nullable. Okay. Now after obtaining the nullable variables, that is nullable non-terminals, I have to change the rules to remove the epsilon from my grammar. Okay. Now let's eliminate the epsilon rule by modifying the existing rule, okay, and using the nullable set. So S gives ATA. So the original rules should be written as it is without epsilon production. So I'll write S gives ATA, and if you observe, T is nullable, right? So T is in the nullable set. So what I have to do is, the other rule what S gives is without the nullable non-terminal, that is AA. So this is the changes what I have to do with the first rule. Okay. Second one, T gives ABC. So this rule I will write as it is, no changes here. Now since A, B and C all three are nullable, I have to make the changes. First what I will do is, I will consider A as nullable, so I will write BC. Okay, so this is by eliminating a nullable A, non-terminal A. Then I will consider B as nullable, so what I get AC. Then I will consider C as nullable, so I will get AB. Okay, now we are not done. Now we have to consider this combination. Since I have more than one non-terminal appearing here, I will take both AB as nullable. So what do I get? I get C. The other case is, I'll consider AC as nullable, so I'll get B. And finally I'll consider BC as nullable, then I'll get A. So this is a modified rule. This is very important. So if I have rule something like this, where I have more than one non-terminal appearing on the right side, I have to eliminate by considering its combination. Okay, so if I had 4, then I get more combinations, right? So this is what you have to remember. Then for the next rule, that is A gives AA. Okay, so I'll write AA as it is. Okay, the other rule what the modification added is without A, right? So what do I get? I get single A. Then I'll write C as it is. Okay, so this is the alteration what I did, and the same is applicable for B. B is this is written as it is. Then I'll write again by eliminating non-terminal B, okay, since B is nullable, and C. And finally I'll write C gives small letter c. So I shouldn't write C gives epsilon. That is the very point of writing this, isn't it? So this is the new modified rule set what I got. Okay, and this is the equivalent grammar for this without epsilon production. So any derivation that will be able to obtain, that I'll be able to obtain from this grammar, I can obtain the same using this modified grammar without epsilon production. But the additional feature is, I don't have or there is a reduced ambiguity in my grammar, right? So since there is no epsilon here, the ambiguity in my grammar has been reduced. I cannot say it is completely eliminated. The grammar definitely more unambiguous compared to this one. Okay. Now there is a question: what if the language itself requires epsilon. Okay, so you consider this example a n b n, where n is greater than or equal to 0. Now what if the case is n is equal to 0? If n is equal to 0, then I have 0 a's and 0 b's, so which will lead me to epsilon. So in this case I cannot eliminate epsilon altogether from the grammar, right? Because the language requires epsilon to be retained. Now we have to identify the ways in which I should have at least or at most one epsilon, right? So I cannot completely remove epsilon from the grammar. So there I need to have some provision of obtaining epsilon as my derivation by having an epsilon rule, but still without ambiguity. So we will see that in the next example. Now let's go back to our original example of balanced parenthesis. Okay. Now let us apply the epsilon eliminating methods to make this grammar or reduce the ambiguity in this grammar. Okay. So what I need to do, again, we have to get the nullable set, right? The nullable set, initially it will be empty, pass 0, and in first pass what will I get? I'll get, let's see. Okay, so yeah, the third rule implies S gives null, right? So that makes S as nullable. Now let me modify the rule. So with the S being removed, I'll get this, okay, a simple opening and closing bracket. Okay, now in this case, if I remove S, then what do I get? I get S gives S, isn't it? So either if I remove the first S or the second S, I'll get a rule something like this, S gives S, and this is meaningless. See, non-terminal giving itself is of no prominence in my rule set, so I can simply eliminate that. Okay, and S gives epsilon is eliminated altogether. So this is the rule set what I get, isn't it? So this is what I get. Okay, so this is a reduced ambiguity version of the original balanced parenthesis problem. But as previously said, what if I have to generate epsilon? So in that case, I have 0 occurrence of opening bracket and 0 occurrence of closing bracket. This is valid as per the definition of the language, right? But I don't have any rule here that can generate epsilon. So what I have to do? I have to retain this epsilon in some way. So this can be done by adding a new starting state. Okay, let me name it as S star. Okay, S star, and S star should be able to give epsilon. And this new starting non-terminal rather, I made use of the term state. Okay, it should be a starting non-terminal. This starting non-terminal, new starting non-terminal, should give S, that is the previous non-terminal. Okay, and the previous rules should be written as it is. S gives opening closing bracket and S gives SS. Okay, so this is the modification what I have to do if the language requires epsilon production. Okay, so when can I say that language requires epsilon production? When the starting non-terminal of a grammar, if it becomes nullable. Okay, so if the starting non-terminal, that is yes, if it becomes nullable, then I should consider that the language requires epsilon production. So in that case, I need to add a new starting state S star, and I have to make an epsilon production, and the new starting non-terminal should give a transition to our old starting non-terminal, that is S. Okay, now will I be able to generate epsilon? Yes. Okay, how will I be able to generate epsilon? Because I have S star giving epsilon. All right, and S will not give epsilon anywhere, so I cannot have cannot generate indefinite number of S and eliminate and wipe it out by substituting it to epsilon. That is not possible. So we have reduced the ambiguity with respect to epsilon production, and we have retained the one epsilon what we needed, right? What is required. So that is done by adding a new starting state S star. Okay, so this is the solution. If I require, or if the language require epsilon production in it, okay, so which is epsilon is a part of the definition of the language. Now we shall see how to reduce or how to remove the symmetry in our grammar. Okay, because only epsilon elimination we have seen, still the grammar is ambiguous because it has symmetry. It has the rule S gives SS, right? So let us see how to eliminate such rules. Finally, we will see how to remove the symmetric rules in the grammar. So do we have any symmetric rules in this particular grammar? Yes, we do, right? That is S gives SS. So if I read the right part here, if I read from left to right or from right to left, I have I'll get the same thing. That is, there exists a symmetry. Now somehow I need to remove the symmetry. This can be very easily removed by replacing one of the S here with S1, right? So what I can do, I can replace this with S1. Okay, so this is a new non-terminal S1, and this, by adding or by removing the S with or replacing S with S1, I have removed the symmetry from my grammar. Okay, now the question is, can this also be written as S gives S1S? Yes, even this can be, this will remove the symmetry from my grammar. But the only difference is the first one will force the branching towards the left of my parse tree, so which we require, right? So when we evaluate opening and closing bracket, we evaluate it from left to right. So if that is the case, then I have to keep this left S as it is and replace the right S with S1. Okay, if I wanted to evaluate from right to left, then I will retain the S on the right side as it is and replace the left S with S1. Okay, so this is how I remove the symmetry. And once I replace this SS with S1, so this is what we will follow. Okay, then I have to make the changes here with my grammar. So what changes I have to do? Okay, so let me rewrite the grammar. So I'll write in blue here. S star will give epsilon. So no changes here. Okay, now yeah, so this S will give SS1. This is how we remove the symmetry, and I have to add one more rule, that is S giving S1. So whenever I make the changes, I have to make sure that this is written in this way. Okay, so you'll get a clear understanding once we see some derivation. And S1, what it should give, it should be able to give S opening S closing bracket, and finally S1 should be able to generate this opening and closing bracket. Okay, so this is the altered rule which will eliminate the symmetry from my rule set, and this grammar after eliminating the symmetry is totally unambiguous. Okay, so first what we did, we eliminated the epsilon rule and we made sure that at most one epsilon is present, so we added this S star. Okay, and finally we eliminated the symmetry from the rule by changing this symmetry or SS to SS1, and the first S, the left S, is retained to force branch towards the left in my parse tree. Okay, which we will be seeing very soon. Then these are the changes what I do. So after changing this S1, I have to write S gives S1, and S1 gives opening bracket S and closing bracket, finally S1 gives opening and closing bracket. Okay, now we'll see some derivation from this new grammar. Now let us derive some valid string from this new grammar, which is claimed to be unambiguous, right? Because we removed the epsilon production as well as symmetry from my grammar. So if I want to generate this, okay, now let me write the parsetree directly. So what rule I have to apply? Obviously, starting state S star gives S, right? And now I will write S gives S1. Okay. After this, yes. Now which rule I have to apply? Again, I have to write S1. So this is, so I am following a leftmost derivation. So I have written S1. This S again need to be replaced with S1. Okay, and finally S1 gives opening and closing bracket. Similarly, S1 here should be replaced with opening and closing bracket, and this will be replaced with opening and closing bracket. If you observe, there is no other possible way of generating this, right? So this is the only method, this is the only parsetree what I get to generate this particular string. So this grammar is unambiguous with respect to this. I mean, with respect to symmetry, and also with respect to epsilon production. Now, if you observe, the branching is forced towards the left, right? If you observe, the branching is forced towards the left. So this was possible by writing this symmetry as SS1. If I wanted to force the branching towards the right, then I should have written S1S. But how do we evaluate opening and closing bracket scenario? We always go from left to right, right? So we have to force left branching. So this is why we have written SS1. Okay. So this is about removing epsilon production as well as removing symmetric rules from my grammar to reduce the ambiguity in the grammar. Okay. Now let's resolve the problem of ambiguity with respect to arithmetical expression problem what we have seen previously. Okay, so the main problem here is not because of the epsilon production, but rather it's because of symmetry, right? So here I have E plus E and E star E. So this, so by changing the symmetry, I can remove the ambiguity with respect to associativity in my grammar. That is 1 plus 2 plus 3. So it has to be evaluated. Since I have operators of same precedence, I have to evaluate from left, right? And previously we seen how I can force branch my grammar towards the left by changing the symmetry with respect to the examples of opening and closing bracket. So the same can be applied here. So what I have to do is I have to rewrite this grammar as E gives E plus a new non-terminal, let me name it as T. Okay. So with this I am forcing the evaluation from left to right. Okay, and T has to be written as, or E gives T. So this is what you have to write. Okay. Now, how to resolve the problem of precedence? That is, since multiplication is having higher precedence over plus, then I have to write a new rule here, and the rule that has higher precedence should be written on the bottom, okay, or it comes in the later part of my rule set. So this is how I impose precedence in my grammar. So I will write T as T star F. Okay, and F, why I have not written T star T? Because again it will impose ambiguity with respect to symmetry, right? So I have written T star F, and F gives, or rather T gives F, I have to write here. T gives F, okay, and F gives opening bracket EF. So this is because everything inside the opening bracket should be evaluated first. So this is having the highest precedence, and where I have to restart everything, isn't it? So F gives opening E closing bracket. Then finally E gives ID. Okay. So with this new rule, I don't have the ambiguity. Okay. So to confirm, we'll take one example. So I'll take the example of 1 plus 2 star 3. Okay. So obviously 2 and 2 into 3 should be evaluated first, then addition should be performed, right? So let's see whether this is possible. Okay, I have to start with E. Let me directly write the parsetree. Yeah, this is equivalent of ID plus ID star ID. Okay, so E, which rule I have to write? E gives, yeah, I have to write E plus T. This is what I'm supposed to write, E plus T. Okay, and T should be evaluated to, or if I am going with the leftmost associativity, leftmost derivation, then I have to replace this E with T. E with the T. Then T gives F, and finally F will be evaluated to ID. Okay. So this is how I obtain this one. Okay, this is about this one. And the non-terminal T has to be again expanded. So what operation we performing? We perform multiplication, right? T gives T star F, and this T is evaluated to F again. F gives ID, which is nothing but 2. This F is evaluated to ID, that is 3. Okay, so writing in this way, what I will get? So here I am performing multiplication first when compared to addition, right? So 2 into 3 is this operation is done, and the result will be stored here, which is nothing but 6. And then I will perform the addition on the result what we got using multiplication, right? This E value is nothing but 1. So what do I get? I get 7. 7 will be returned here. And if you observe, there is no other way of obtaining a different parsetree, right? So this is the only parsetree that is possible, and I'll get the expected result. So there is no other way of getting different results or different way of evaluation. Okay, so writing the rule in this way, we have solved the problem of left associativity by making sure the grammar is not symmetric. Okay, and we have changed the right non-terminal here, right? So this is because I have to force the branching towards the left, which we have done here. I'm forcing the left branching, and this solves the problem of associativity. And writing the rule with respect to multiplication here lower, right? So this will induce hierarchy. Okay, so this will add precedence to my grammar. Okay, so by applying these two techniques, I have resolved the problem of both associativity as well as precedence in my expression. Okay, now this grammar is unambiguous with respect to evaluating an arithmetical expression. I'll see you in the next one. Thank you.